Hello, everyone. I'm Renee, if you don't know me. I'm a PhD student here at UMaine, and I'm gonna take you on a twisty, turny journey through my PhD research and the kinds of questions that I'm thinking about on the ice field. I have not great transitions between the two, so if anyone has like great questions or discussion, we can totally chat later. I totally realize that I have been thinking about these questions for a lot less time than folks who are on Zoom and in the room. Okay, so kind of orienting ourselves, we know glaciers are retreating, we know we care about the Juneau ice field. Alaskan glaciers are retreating the fastest out of all of the other glacier regions on Earth. And we also know that we care about this connection between our glaciers and our downstream. And so thinking about sea level rise, thinking about downstream nutrient transport from salmon fisheries, ocean circulation, and things like that. And so what I'm thinking about as part of kind of the first part of my PhD is, can we quantify how much water is being actually stored within the ice, which kind of serves as this modulator for downstream effects. And so focusing in on North Basin, this very small little semi-enclosed ice basin along Taku Quonset or Taku Glacier, along its lateral margin. It's a very small basin. It's about 1 kilometer squared in area, and it's quite easily accessible because Camp 10, which is where the JERP grad program will be, lives right up the hill from it, one of the permanent JERP camps. And so, as I talked about a little bit or alluded to, some of the motivating questions for this part of my PhD is first, where is subglacial liquid water stored in North Basin? And then two, can we use ground penetrating radar to identify where this subglacial water is? And then this research is also, like, the goal of this was to eventually select a drill site for the NASA drill test that occurred in 2025, which I'm sure you'll hear more about from Jill, who I believe is giving her talk next. And so this is an awesome aerial photo of looking down into North Basin by Newt in 2024. And so one of the things we think about for North Basin, and one of the reasons that this original NASA funding happened, is because there were these kind of persistent concentric crevasse patterns in the top corner of the basin. So, like, I don't know if my mouse is going to be helpful. No, it's jumping around. Awesome. And the thought, there's a pointer? No, now I'm flustered. It's okay. So the thought here was these concentric crevasses would form annually and be consistent with subglacial water cooling and causing that ice surface to raise up. And so what we're seeing, I think, in more recent years, and would love to hear from folks on Zoom and in person who have been there recently as well, is we're seeing crevasse patterns that are potentially different. And I think this one shows a really good example of, we have some of these more major, like, radially propagating crevasses from this corner. It's right near a superglacial lake that forms annually. And then, as I mentioned, we're connecting into the Taku Glacier and our dominant ice flows to the south here. So North Basin, very small basin, really hydrologically dynamic and potentially still confusing despite all of the data that we have collected. And so by now, we've probably collected about 150 kilometers of radar data just in North Basin. And so I'm going to focus today on the 2024 data collection that we completed with this 10 megahertz radar. This is a common offset radar. So we have our transmitter sled in the back that sends our signals into the ice, and our receiver sled in the front. And that's also the black lines in this image on the left. And so we collected about 70 kilometers of 10 megahertz data and processed it, picked the bed reflector, and then this is our plot showing bed depth in North Basin. And so we feel okay about the way that we selected our bed reflector. It gets really complicated in these basins because the subglacial topography can cause off-nadir reflections in our radar data. And so we need to be really careful, like selecting which reflector we believe is true bed. And so the results show that we have depths ranging from about 50 meters down to 300 meters in the middle. That's fairly consistent with what we would expect in this kind of geometry. We have deeper depths towards the middle and shallower depths as we approach the walls. And we're also seeing relative line-to-line depth consistency as well. And so these data were collected throughout June. So these are all of the June data from 2024. And so we're seeing line-to-line consistency for our perpendicularly crossing lines as well as through time, which is also like really good. Okay. And then what I did next was take our bed depth and take our basal power. So this is the amplitude or the power of the response at the bed, and corrected the power for our depths. So we want to correct for the amount of distance our radio wave is traveling through the ice, because that impacts our bed power. And so also just to note, I'm not correcting for end glacial attenuation here. I'm really only interested in relative comparisons. This is a temperate ice field, and so it's very warm and very wet, and we kind of assume that all of the ice is at 0 degrees Celsius, but would love to chat if anyone has ideas on this as well. And some of the things that we notice are potentially some linear patterns where we have relatively higher power than other areas. And this is, again, interesting because they're consistent line to line and through time. And so from that data, we selected our drill site for 2025. On the left is the profile in the top showing we selected the drill site as a team about 2/3 of the way across the basin from Camp 10. And then this is our radargram showing that selection. And so you can see like we have these multiple reflectors going on, and that's kind of true for most of them. And so what we're consistently selecting this lower reflector. However, this is kind of where they converge. And so we felt, I guess, okay also about selecting a drill site there for our depth estimates. And then this is a photo from our mountaineer Brian from up on the mountain looking down at the drill site. You can see our super glacial lake still in this back corner. And this was a pretty high snow year this past year, so still lots of snow along the rock there. And so some of our results and interpretations, this is our drill site here. We selected it because it was about 300 meters deep in the depth plot, but also a very small, like higher power area. Maybe it wasn't an outlier and that just like is water. But some of our results show that from the drilling that there was water at the bed, and they drilled 300 meters to the bed almost exactly. And so we felt pretty good about our ground truth there. And then I guess some things to think about too for these kind of linear higher power areas in North Basin. They look kind of like what you would expect if you were looking at like a potential like subglacial drainage pathway. However, I'm not sure if we can fully say that right now. I think it's possible, like we either have higher power at the bed, or what we have is just less ice column scattering, which we can't really correct for because we know we have liquid water like prevalent throughout our ice column, and so we would get that scattering. But yeah, happy to chat about this with anyone. And then I think we're moving into the, oh yeah, okay, I have a summary slide. So where do we go from here? Back to our questions, where is subglacial liquid water stored in North Basin? Potentially we have these subglacial drainage pathways, or we also just have water everywhere, which is also a possibility. And then can we use ground penetrating radar to identify subglacial water? Yes, question mark. I think it's quite challenging in these temperate environments, but potentially this is possible with really high resolution data sets like the one that we have here. And so from here, I'm going to transition. Oh yeah, awesome. This is what we were just kind of talking about. So the hope is we have a collaboration with UMaine and Swansea University this coming summer. You'll hear from Jess in a little bit. And the goal here is to essentially ground truth a bunch more points in North Basin and have a better characterization for the subglacial hydrologic conditions. And Scott mentioned outfitting boreholes with sensors. So again, open to on that as well. And so the hope is really to just kind of understand hydrologically what's happening in North Basin, despite it being very small, but still a very dynamic system. All right, and so how am I at for time? Sure. And so I want to talk a little bit, diving into some of the like very, very preliminary work that I've been thinking about as part of the next section of my PhD. On the left is just a list of prior work that I've been thinking about. This is not a comprehensive list of prior work, and so please point me in other directions if you have other ideas. However, one thing to note is in 2015 to 2021, they flew airborne radar across the Juneau ice field as part of Operation Icebridge, NASA's project. And all of these black lines in this figure by Brandon Tober show where the lines were, and all of the ones with color show where we could see bed. And so they're not from the airborne radar. It's really difficult to interpret bed across the ice field, especially because we have so much clutter from off-nadir reflections from surface topography. And so in 2025, a master's student in our group, Mari Fromstein, she finished her master's comparing modeled ice thicknesses from the Farinati papers with radar data that we had collected across certain parts of the ice field. And so this is an example on the left showing the modeled thickness in this teal line, and then what we interpreted as bed in the 5 megahertz radar line, which you can see is hundreds of meters different. And so she then created this plot outlining RGI boundaries, so delineated Randolph Glacier inventory boundaries, and where there are ice divides along the ice field. And we used this to target a bunch of surveys in 2025, this past summer. And so motivating questions for this work: how thick is the ice? Realizing this is not a novel question. Many people are concerned about how thick the ice is. But I'm concerned with how do we reduce uncertainties in radar-derived ice thickness in a temperate alpine environment? And also, can we use ground-penetrating radar ice thicknesses to reduce uncertainties and estimates from other methods? So how do we use methods together, and how do we say which one is more uncertain if we're comparing the two, I guess, without a proper ground truth? Okay, so this is the data we collected in 2025. This special thanks to Michael Christofferson for teaching me how to use it and going out on a bunch of surveys. And then Jack Holt and Martin Trufer have components of this Frankenstein radar that we dragged around. It's about 200 meters long, dragging behind the snow machine. So you got to make really wide turns. And so you can kind of see in this photo, it was so hard to photograph. The top sled way in the back is our transmitter, and this next one is our receiver. And so we collected about 250 kilometers of 1 megahertz radar data across the ice field, really targeting these parts that Mari notified us of, but also just trying to get kind of like cross sections along the glacier. And some very, very, very preliminary results. These are preliminarily processed, they're not migrated, and there's certainly more processing to do to kind of pull out more of our signal. But this is one profile going across Taku, just south of Camp 10, and I think we can see bed fairly clearly in this one. And then this is a profile up near the Mathis-Llewellyn divide, and we can see bed fairly clearly down to about 1,100 meters in both of those profiles. And so some of these profiles we feel like okay about interpreting, and then other ones look like this, which I think is more challenging to interpret bed because we also know we're getting a lot of clutter from surface topography and subglacial topography. And so both of these lines are this is from across Taku. You can kind of see North Basin at the top. And then this one is from where the Demarest branch converges into the main branch of Taku. So some challenges, like I mentioned, we have surface and subglacial clutter. This is work that Michael Christopherson is working on and shared, and so these are called clutter simulations. And so what it does is it takes a surface DEM and then it models how much clutter we would expect to get from radio waves bouncing off of that surface topography. And so this is our profile here. So going from Camp 10 up towards Echo Glacier, and you can see the white parts are that surface topography that's most impacting our signal. And then that's what we get here. So this is called a cluttergram, and this is essentially the model of all of the clutter that we would expect. And then what we do is we compare this with our radar profile, and we look for things that aren't the same. And so at the very top of this profile, there's this section here that we think is potentially true bed and actually not cluttered. But we have a lot more work to do with looking at these cluttergrams for sure. And then another challenge that we ran into was interference from Juno AM radio stations. And so on the left is showing a frequency plot of one of the radar lines that we have, and these spikes are like very exactly coinciding with the frequency of these three Juno stations. Talk radio and greatest hits are not great for us, unfortunately. And so not necessarily like causing a huge amount of interference. Like I do think our biggest problem is just clutter. So like our reflections bouncing off of different rock that's not bed. But certainly something to think about, and if anyone has other ideas, happy to chat. And then finally, this is kind of half-baked ideas, but would love to kind of pose some questions as well to folks for discussion. So on the left is a deep radar profile traveling from across Taku into North Basin. And then on the right is a similar profile, but traveling into Icy Basin, which is that basin just on the other side of Camp 10. And so what we can see in both of them is we have a little bit of an over deepening as we go into the basin. And I think for me, that makes it very exciting for storing water at the bed. And so I think this could potentially be a really interesting problem as we think about dynamics on the ice field as a whole. And so here's a bunch of questions. I won't go through them super in depth, but I'll leave this up for folks to perhaps ponder if you are excited about it. But we know, like looking at the Juneau ice field, there are several smaller semi-enclosed ice basins that exist along the lateral margins of major glacier trunks. And so I think we're wondering is if we have water that pools inside of these basins potentially, do they reach some sort of threshold where that upward force causes the water to drain out into the main branch? And how does that impact ice flow? Like if we have a bunch of water that we've just punched into the lateral margin of a glacier, how does that impact ice flow and future glacier velocities on the ice field? And so that's kind of where things are going, which is a bit of a combination between thinking about North Basin and then thinking about full ice thickness. But that's pretty much all I want to talk about today. So I'll thank, obviously, JERP Logistics and staff who had to sit on the snow machine with me for 250 kilometers of radar data. Like, thank you very much. As well as all the folks listed here, funding sources, and everyone that is obviously not pictured as well. So thank you all. I'll take questions or comments. Yeah. Keegan sent to Hart. Yeah, Peter.
You have a good kinematic control of the surface. Good kinematic control.
So in the basins, it doesn't really move much. And so are you thinking mostly about this last problem that I posed? Or?
No, but all of it really, and starting with your some of your crevasses and the changing strain rate of this surface.
Yeah.
Indeed.
We don't have much. I think like GPS stuff would be really useful for that. And then obviously we have the TRI, which I think the hope is also to install that looking over. They have some preliminary stuff from the TRI looking down into North Basin, but not that I've worked with. But that's a good question. Can be more discussion too. Yeah, so
The radio station, I got thinking like, well, we could probably bump up a little higher frequency. What did we use for frequency last year?
one.
Yeah, I wonder bump it up to 2.5 or 3.
Yeah, we could totally do that. Yeah, for sure.
Jack or Mark have that higher, we can find someone to build.
Yeah. Or we could also, like, I don't know if you've tried the 5 megahertz with the high power transmitter.
I have, I think we've maxed out at about 800 meters.
Okay.
Maybe 900 meters. I think some of the work that, well, yeah, you did, didn't you? Wasn't that?
Yeah.
Didn't you collect 900?
Yeah, but not at Taku.
And I'll talk to you.
But yeah.
So we could try it, but I'm not sure we'll make it those
Yeah.
next steps.
But yeah, we can totally chat with them. Yeah. I see Brad online. That's fine.
Yeah, hey, thanks for the great talk. I had a related question, which is, well, it's kind of funny to see the interference from their local radio stations. And I was wondering if you all are transmitting with enough power that any of their listeners ever complain every June about.
Yes, yes, Brad, we certainly are. I would love to try if anyone is in town in Juneau and wants to turn on the radio and check, but I asked Michael, I was like, hey, like, what stations do you think we're like interfering with? And he was like, oh, we're saturating all of the frequencies. So anyways, hopefully not the airport. Kaya, I see Kaya with a hand.
Yeah, totally. I was just curious. So you had those like potential subglacial pathways, and you had like a bright spot within it, which is where the drilling happened. Have you looked at like, is that a hydropotential low, or like are those channels possible? Like, yeah, have you done the like hydropotential routing through that area to see like, are those places that we would expect there to be channels or not?
Right. Yeah, that's a good question. I haven't like quantitatively looked at it, but looking at the depth plots, it doesn't really appear that there's like very clear lows. I also wonder if it's potentially like outside of the resolution of the radar. Like if we do have like very, very small lows, we would still get water collection and we might not pick that up with the depth, but then we'd still have water impacting the power. I don't know if that
Yeah.
makes sense. I'm not sure though. Yeah. I don't think I feel great about saying that there are hydraulically potential or low hydraulic potential there.
Do you feel better about there's kind of just water everywhere?
I guess. I think there's water probably more places. And so one thing I guess concerned about for the ground truthing is that we're just going to hit water everywhere. And is that not really going to answer these questions about like discrete locations of water? And so I'm kind of hoping for like dry bed in some of the areas because I think that would be helpful. But also if it's all wet, then potentially it is just showing us that we have some sort of end glacial scattering that's impacting our bed power more than the actual bed. Yeah,
Cool,
thanks,
thanks.
Kaya. Yes, I see William Armstrong. Hello. Billy. Hello.
Yeah, and sorry, I mean, there's people in the room too. It's we can't see if anyone's raising their hand, but I'll assume that there's no one in the room if you're calling on Zoom people. Um, the basins thing is really cool that you were showing, and I guess I was wondering as like a zoomed out sort of question, like I mean, you were showing in other places that the bed is like 1,100 meters below the surface, and I feel like I've heard so much about the flat upper ice field that as the snow line rises, like that it's the ice that's providing topography there. And as we continue to thin through there, like are these basins potentially places that could be like ice refugia in a warmer world where the ice surface in the high ice field starts to come down? Could these be places that ice is held on to the longest, or does it seem like there's not enough accumulation area above them that they aren't necessarily like an ice refugia sort of thing? Do you have any thoughts on that, or have you pondered it yourself?
I have not really pondered it. That's a really good question. I imagine where we're above the ELA, like those might turn into kind of more like potentially little like cirque glaciers as we start like lowering ice surface. But I do think that at least down in North Basin, potentially like just ice lost. I don't have like great mass balance on like specifically like North Basin and Icy Basin, but yeah, if anyone else has thoughts on that.
I know that's below the current ELA,
Mhm.
North Basin, but you know, maybe you'll have something like that up with the Divide area or
Yeah.
northern Northwest Branch or something like that.
Yeah, I'd be really interested to kind of test this theory on some other basins around in the northern parts of the ice field for sure, or higher elevation.
Some of your like the exposure age stuff might be able to tackle that too.
Oh, that's a good idea,
Especially
yeah.
when you get under the modern ice and take a rock sample if it's,
Yeah.
you can see it happen in the past and then there you go.
Love it, yeah. Yeah, all
We
right.
have to deal with the erosion rate too, is that right?
There's a lot of problems with it.
Someone else can think about the Cosmo problems and they can.
Jake, you are designing a like sampling mechanism, right? Or we're getting a sampling mechanism?
I've got a rock sampling prototype, and I'm looking at if I ever can get enough funding, some commercially available models that we can outfit for our hot water drill boreholes. But basically I have electronic architecture up right now that I'm sort of perusing as we're talking about this, because there basically no end to the number of devices we can outfit that system with. Whatever anybody's interested, we can probably build a sensor or a device that we can integrate.
I think you and Jess are gonna be like best friends on building devices.
Cool, damn, yeah.
So can you go back to some of your transects across Taku? So I'm not an expert at
Like these ones,
interpreting radar profiles,
for sure.
but like the one on the left, you said, oh, it's quite a good. No, it's something in bed. Where's the bed?
Okay, so essentially what I'm looking at here is like these really steep and straight lines are cluttered, most likely. And so I'm kind of ignoring some of these ones down here, and I'm looking at this line that's going across that's like a little less like perfect and regular. And also I'm looking for like it deepening in the middle, because I know this is going across Taku, and so like we should have some sort of deepening in the middle. But yes, this is a really good question.
So you have an expected depth,
Yes,
and
exactly.
then you see something like that, you say, okay.
Yeah, and like the expected depth for the middle of Taku is like much hot. Like we didn't really get, so profile 4 is like the famous profile that's like they like up to 1,500 meters depth, and we didn't really get a good profile for profile 4, unfortunately. And so maybe we could this year. But another good example of that is like this line is going across the divide about. We see a pretty clear bed here, and like we know it's like higher accumulation area, so like less melt. And so we don't see as much of that like near surface like messiness or scattering. And so I feel like much better about interpreting this one even than I do the left one. But yeah.
So on that left one, all that structure between, the surface and 400, is that liquid water interference?
It could be. It also could just be like if we have any sort of like electrical change, so any sort of layering. However, like this is a really low frequency radar, and so we're not going to be able to like resolve stratigraphy in the same way that like Kaylee's work would.
So I guess that's my question, like with that low frequency and that power, can it like blast through the water? See through it?
I mean, yeah, it can at least like looking at those, but I think, yeah, I don't know. I still think that maybe the clutter is the bigger problem. So like hitting other mountains before we hit bed is even a bigger problem than like liquid water scattering. But yeah, not sure. We'll see. Yeah, good questions.
One thing that comes to mind is just, Atsu, I think we'll talk tomorrow, but, like designing co-located profiles
For
with,
sure.
with radar and gravity and seismic profiles, short of Kaya leaving and living in Alaska to get her blasting license in Alaska. It would be nice to have, some future co-located lines on the ice field that are, like targets based on like what you've designed here. And I think the other question I have is, and maybe this is what Peter was alluding to, thinking about if we have good velocity constraints, kinematic constraints on the ice, doing similar to what Brandon did on Ruth Glacier, where we have some ice thickness measurements and then modeling those environments that we are really struggling to get good constraints on.
Yeah, for sure.
A worthy path forward.
Yeah, totally. Chapter 3.
Yeah.
Good stuff.
PhD, post. Yeah, post.
Sounds good. All right. Thank you all.
Thanks, Renee.